Wahyu Bambang Udayatno from High Resistant Materials Research Group of Research Center for Physics, and I will be serving you as the moderator in this webinar. In this occasion, we shall have outstanding presentations from our prominent presenters, whom I believe shall enrich our insights and knowledge regarding the topic of this webinar. Now, before hearing the presentations, I would like to ask Dr. Rico Yudianti, as the Director of Research Center for Physics, to give her welcoming speech and officially open this webinar. To Dr. Rico Yudianti, the floor is yours.
Terima kasih Pak Wahyu. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Good morning, ladies and gentlemen. My distinguished speaker of this seminar, Dr. Felix Teska from School of Material Science and Engineering, University of New South Wales, Australia. Mr. Bravola, I hope already joined with us this morning from Thermic Coating Industry, and our researcher from Research Center for Physics, Dr. Sugiarti, who belonging to our research group of high resistance materials. Thank you very much for all invited speaker. You're willing to be invited speaker in our seminar today, and welcome to all participants. Very happy to meet all of you. This seminar is not meaningful without your participations. This is our fourth seminar we already held by our research center to promote our research group with the relevant topic as important issue to be discussed. And today, superalloy is our main topic of the seminar, and have excellent properties in mechanical strength, thermal resistance, good surface stability, and resistance to oxidation is considered for this main component for gas turbine. Today, our invited speaker who have expertise and experience on development of this structural material design and how to analyze its microstructural degradation propagation and its potential application for turbine blade will be interesting topic to be discussed today. Hopefully, this seminar will give us insight, knowledge, and sharing experience from our invited speaker, as maybe as seed collaboration among us. And thank you again for our invited speaker and participants. Last but not least, thankful for all members of High Resistance Material Research Group to well organize this seminar this morning. I think that's all my remark this morning. I hope and enjoy of this seminar. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Dr. Rico Yudianti, for officially opening this webinar. Now we can, ladies and gentlemen, we can enter the webinar session. And before the presentation begins, please allow me to introduce our three prominent presenters. The first presenter is Dr. Felix Teska from Schools of Material Science and Engineering, University of New South Wales, Science, Australia. Please correct me if I'm wrong. He has published many publications here on microscopy studies, I think, particularly on alloy research. And we also have the second presenter will be Mr. Bravola A Bancin from Thermic Coating Industries, Indonesia. He is a professional material engineer who possesses a lot of industrial coating experiences. And for the third speaker will be Dr. Sugiarti from Research Center for Physics. She is our excellent researcher who has conducted many researchers on today's topic. And for the first session, I would like to ask Dr. Felix Teska to give his presentation. Dr. Felix Teska, you have about 45 minutes to present your presentation, and after that we can go through the discussion session, and after that we can step further to the next presenter. For Dr. Felix Teska, time is yours.
very much for the introduction. Let me just maximize these slides. I hope everyone can see the right view.
Yes.
Great, thank you very much. At this point, I also want to thank Andy Sohandy and Dr. Annie Sugiarti, who invited me and organized this talk. I very much appreciate this. My slides are about the high-resolution characterization of the nickel-based superalloy alloy 718. And that's pretty much an overview of the work I used to do here at the University of New South Wales in Sydney as part of the engineering microstructures group of Dr. Sophie Premick. We're working on one hand side with superalloys, so I'm part of this part of the research group where we look into alloy 718, Rene 41 and Udimet alloys. And on the other hand side, we're working on additive manufacturing of titanium alloys, also superalloys in different grades of steels. I want to start with a motivation slide, give a brief outline, followed by sections 3 to 6, which are basically 4 papers that came out of my research studies. So these results have been published, and if anyone wants to look them up, you can find them online later, and then close the presentation with a summary slide to wrap it up. Okay, as a motivation, since 2016, 1 million passengers are traveling in airplanes at any given time now. We're all aware that these numbers probably have changed now due to the COVID situation. But if we look at the history of the aviation sector, it bounced back from pretty much any major crisis happening and consistently doubled the world traffic every 20 years. What this also means is just Airbus alone expects about 37,000 new aircrafts to be delivered until 2038, I believe is that. So there's a huge demand for this. And at the current time, the aviation industry contributes about 1.5% of the worldwide carbon dioxide emissions. And this comes with a couple of challenges. For example, there's been new records broken with aircraft range, but we don't want to travel equally longer, so the airplanes need to fly faster. The sector relies heavily on fossil fuels, which are very limited, so we need to deal more efficiently with them. And as we emit carbon dioxide, sea ice is usually lost. So there's been a couple of studies on that as well. And there's a few approaches to tackle these challenges. One would be to make the aircraft lighter using lighter materials, but on the other hand side, we also need to create more efficient aircraft engines. And we can go the way of developing completely new alloys. But because these are aircraft materials, they need very long accreditation processes. So if we start a new alloy this year, it would take up to 10 or 15 years until it can be used. A more streamlined approach here is, sorry. Okay. I just continue. A more streamlined approach would be the advanced processing of existing alloys that are already well established, such as alloy 718. And that's a polycrystalline and precipitation hardened nickel iron based superalloy, and we would find it in the turbine discs, in the high pressure and low pressure sections of aircraft engines or even gas turbines. As we look into the microstructure of this alloy, you find a face-centered cubic gamma matrix. We find delta phase platelets that are rich in niobium. They are usually in the size of a couple of micrometers, so they're fairly large and decorate the grain boundaries. And then most importantly, we find 2 types of nanometer size precipitates that are gamma prime, which is rich in aluminium, as well as titanium, and gamma double prime, which is rich in niobium. And this gamma double prime precipitates contribute the a major part of the strength for this alloy. Right, so we can look at the aircraft engine at the top right corner, and I just put a red box, but it's actually talking here is basically the hottest parts of the engine. You've seen the chemical composition is quite complex for this alloy, and therefore the strength contributions are also quite complex. So we have the intrinsic yield strength, we'll get some grain boundary strengthening, that's our hull patch relationship, we get some solid solution strengthening and work hardening, but most importantly is the precipitation strengthening. As you can see, it contributes about 44% of the yield strength. To narrow it down a bit further, my work was mostly on direct aging of this alloy. And there has been some previous studies. This process is not completely new. So what's been shown is that the yield strength can be increased by 10% just through using this different process, while having equivalent creep and low cycle fatigue resistance. So there are no major trade-offs when using this process. What we also know already is that the delta phase volume fraction is lower and we have a higher dislocation density. When we look at the temperature range of conventionally high strength 718 compared to direct aging of 718, we find quite a major improvement. All right, let's start with the first part of my research, which was a comparison of the conventional versus the direct aging of alloy 718. And with conventional aging, I mean, after forging, the material is solution treated, followed by an aging process, which is usually done in this two-step aging. Whereas direct aging means we skip the solution treatment completely and the material is aged just after the forging. And if we want to study any differences in microstructure, we would start by comparing the as-forged condition, the solution treated condition, and then the final conditions, direct aged and conventionally aged. Great news, we could actually reproduce this increase in yield strength as well as ultimate tensile strength. But if we also look at this time temperature schedule, we see the overall process is shorter and makes the manufacturing of turbine discs more economical. Starting with the grain size, I used some EBSD and electron microscopy to have a look at the grain size, and we see that after direct aging, the grain size remains very small, whereas after the conventional aging, we find some selective grain growth occurring here and there. In the bottom left micrograph, you see these white platelets in the gray gamma matrix. This is our delta phase, and because we have this really nice contrast here, we can start to quantify this as well. So here it's highlighted in red, and we can compare the delta phase volume fraction. And again, we see that the solution treatment does increase the delta phase volume fraction, whereas after the direct aging, the delta phase volume fraction remains lower. Now we want to have a look into the dislocation density, and we have a look at the as-forged condition. So on the left-hand side, we see a EBSD map, but only reconstructing the geometrically necessary dislocations. You have to ignore all the grain boundaries. They just show up in green and yellow, but rather focus on the grain interior. I can get a laser pointer. So we're looking at these regions here, and we see that there's these dislocations progressing far into the grain interior. And we can confirm this with TEM imaging, like here on the right-hand side. If we follow the conventional processing, that means dissolution annealing and then aging, we find that after dissolution annealing, dislocations are still there, but we find less of them, and the grain interiors become mostly free of dislocations. And even after aging, now we have these precipitates overlaying in the contrast, so it's very hard to find any dislocation structures at all. We compare this to the direct aging. Again, in the EBSD map, we find that there are still some dislocation traces remaining in the grain interior, and in the TM we can see, although there's a lot of precipitation happening, we also see these dislocation structures. So they are far more pronounced, which is in agreement with previous research. What's difficult though with the TM is to distinguish between these two types of precipitates, gamma prime and gamma double prime. And here the Atomprobe helps us a big deal because we can separate them based on their individual chemistries. So if I move on the top hand side, we see a conventionally processed alloy, which is solution treated and aged. And as we let it rotate, we see that these 2 nanometer scaled particles actually occur together. So we see a gamma prime and gamma double prime sit together. And if we look in more detail at, for example, the duplets and triplets, we find that gamma prime likes to sit in the center of these particles, or is the larger part. On the first side, the direct age material looks very similar. Again, we find these particles sitting together. But if we look closer in more detail, we find that now gamma double prime likes to sit in the center or to form the larger part of these particles. The highlights should pop up. Yeah, as you can see here, these triplets, and here the duplets. Okay, now we already have some insights that this different processing actually changes the structure of these precipitates, and we can summarize what we have found out in this sketch of a microstructural model, where we start in the S-forged condition, where the matrix contains high dislocation density and very little delta phase. If we do a solution treatment to the material, we increase the delta phase, which is rich in niobium. So it takes niobium from the gamma matrix, but we also annihilate some dislocations. And this condition favors the gamma prime precipitation, where we find it as the center particle or the larger particle. On the other hand side, during direct aging, we retain the high dislocation density and a lot of niobium in the matrix, which favors the gamma double prime precipitation. So we find this phase as the center particle or the more larger particles. Okay, if we combine this together with the smaller grain size, a higher dislocation density, more niobium in solid solution, plus these changed co-precipitates, we find there's contributors or contributions to this increased yield strength from all 4 factors. Okay, so the next part will be about the Atomprobe microscopy, how we get more quantitative results. And I just want to use this as a short introduction to the method, just to touch base with everyone, that we know the fundamentals, how it works. So this nice animation, we see we need a very sharp needle-shaped specimen, which is placed in front of a ion lens or local electrode. And after this local electrode, we have a 2D detector. And then we can detach individual atoms by laser or voltage pulsing. And these atoms are ionized and then accelerated towards the detector screen. So from this, we will get a 2-dimensional map, X and Y, where our ions used to sit in the material. And if we record the ion sequence, basically where does the first or the 100th atom sit, we can also reconstruct the Z coordinate. Now you can see because we pulse and then we can measure the time of flight, we also have a mass spectrum in the Atomprobe, which is very convenient because not only do we get the X, Y, and Z coordinates, but also the type of element where it used to sit. And then we get these very nice three-dimensional atom maps. Okay, so this is just a sketch of what we just have seen in case the animation wouldn't work. How we get these very sharp needle samples is quite well established. For example, for these bulk samples, we would start slicing them and then cutting them into smaller rods, as you can see on the left-hand side, and then electropolishing them, such as on the bottom side. That's done with these rods placed through a micro loop with an electrolyte. And if we electropolish long enough, they will approach a tip shape, which is indeed very sharp, as you can see in this SEM image. Okay. Now I said we get the X, Y, and Z coordinates, but the coordinates we record are not necessarily the actual coordinates. So there's a fair bit of reconstruction necessary to get to the true coordinates, or as close as possible. And the two main reconstruction parameters is on one hand, the image compression factor. For example, if we know features in our data set, in their location, such as some crystallographic information, and they do not overlay with the actually observed location, we can correct this. And that's just done by this rather simple ratio. On the other hand side, we have the so-called field reduction factor. And that's a bit more complicated because it depends on the specimen geometry and the resulting electric field. And often the exact specimen geometry is not known, so we can only approach this factor as close as possible. But that's then calculated from the voltage, the tip radius approximation, and the measured electric field. Okay, so starting with voltage mode Atomprobe microscopy, that means we detach atoms by voltage pulsing. We can exploit crystallographic features in the data, and that's then called Atomprobe crystallography, and a whole different other research topic. But we start the reconstruction with such a voltage curve. You see on the bottom the ion sequence number, which tells us the number of each ion and the voltage it evaporated. And you see the very first atoms to evaporate, they took very little voltage, but then the tip becomes more blunt and we need a higher voltage. So we avoid any tip fracture and then have a look what the detector has seen. Remember, that's this two-dimensional detector, and we see there's some regions that give us less signal. And sometimes that can be crystallographic regions, like in this case. We then have a look at the mass spectrum and can assign each peak an element. And once we have calibrated these reconstructions, we get these very nice 3D element maps. Okay, so that's quite nice for the voltage Atomprobe microscopy, but the problem is here we usually need a quite high voltage, which means there's a high risk of fracturing of our sample. And when the tip fractures, the experiment is over, and that's all the data we get. We need to make a new sample. If we want to quantify these precipitates, we need relatively large volumes so we get some good particle statistics. And here we can use laser Atomprobe microscopy, where instead of voltage pulsing, we pulse a laser, which requires a lower voltage and therefore less risk of tip fracture. So again, we see a voltage curve like this, we get more ions. But if we look at the detector map, we see that these crystallographic features have disappeared. That's quite typical for this. The mass spectrum has changed a little as well, but we still can assign all our elements without any problems. But we still don't know what are our correct reconstruction parameters. So we need to find a way to do this. Just a short slide on the laser energy is here. We cannot use any type of laser energy. As you see on the left-hand side, a voltage mode, and on the right-hand side, a very high laser energy. So if we go too far with the laser, we may even distort the resulting data, which is then not useful anymore. What we did here was have a look at the mass resolution and different charge states to calibrate the laser energy, and then could use actually 50 picojoules for this material and this microscope design. Okay, let's move on to the reconstruction parameter calibration. And what this slide is showing you is basically how we use the precipitate morphology. So we start with a voltage mode data set where we can see these gamma prime, gamma double prime precipitates. They have a certain shape, X in X, Y, and Z. And then we can give the relative spatial extent of X, Y, and Z to each other. And as we play around with the reconstruction parameters, we see that we can either stretch or compress these particles. And because it's the voltage mode, calibrated data, we know what is the correct shape of these particles. Now we can take our laser-assisted data and do the same. We play around with the reconstruction parameters until our relative particle shape fits that of the voltage mode. In this case, I put some red boxes here for the appropriate reconstruction parameters, and you see these relative size of the particles are very similar to each other. Okay, now we have reconstructed our data. The next challenge is how do we represent these particles? Because what we see is usually just points of each atom. And what we see here in these brown and turquoise surfaces are so-called isosurfaces. And basically we can do with them whatever we want. We can set them to, for example, 10 atomic percent niobium. Anything above this value will be enclosed by this surface. But how do we know that this value is a correct value? Because if we make it larger or smaller, we can also make the particles appear larger and smaller, which is of course difficult if we want to have an accurate size of them. What we can start with is we look at fully captured particles, such as here. We just chose a random isosurface. We just want to know where are these particles. So we plot them here, and then we put a region of interest. This is a cylinder which goes right through the duplet particle. And then we can plot a concentration profile. You see in figure B, C, and D, I've done this for nickel, aluminum plus titanium, and niobium. So the colorful graphs are the concentration profiles. Now we can plot a differential concentration profile, which tells us the difference between each step for this concentration profile. And what this tells us is the point of the highest concentration gradient, which should be the particle matrix interface. And you can see this works really well. We get global maxima and minima and can use them now as a threshold to accurately represent our particles. And that's the values I acquired for up to 10 particles here for the gamma matrix. For the gamma prime precipitates is about 10.5 atomic percent aluminum and titanium, and gamma double prime precipitates is anything larger than 13 atomic percent of niobium. So we have reconstructed our data. We now can represent these particles reliably, now we can start doing some quantitative analysis of these Atomprobe data. We just, yes, here. So for example, in this figure A, we see the side view of a three-dimensional data set, and that's quite difficult to analyze if we want to know how are these co-precipitates stacked together. What we can do to make it a bit more simple is take some cross sections. We just cut a slice out of our data and then start segmenting what's gamma prime, what's gamma double prime. So we get a much simpler map as in figure B. Once we've done this, we can start counting what are single particles or monoliths, what are duplet particles where two sit together, what are triplet particles or even quadruplet particles. And once we're done with this counting, we can compare them. You see in these different colors, we have these different morphologies sitting together. And what we have observed before is basically represented here again, where SA represents our conventional processing, where we have much more of these triplets with gamma prime as the center, and DA, after direct aging, we actually do have more triplets with gamma double prime in the center. But we can also extract all other sorts of information from these particles, such as volume fraction, the particle radius, particle density, and even the triplet stacking sequence we can quantify. So for example, if we look at the volume fraction on figure A, we do see there's more, significantly more gamma double prime after direct aging. The gamma double prime particles are also larger. The particle density has not really changed that much. But if we focus only on the triplets, we do find this inverted stacking sequence just by looking at the interfaces. Alrighty. Now that's now we have developed a toolbox to analyze these particles, and we can apply this actually to look into actual turbine disks. So what you see here is a result for the cross section of a turbine, right? We look at the slice taken out of a turbine disk. And if we focus here on this middle section, we do find there's some yield strength anomalies, mostly in this middle region where it's very low. And we can reproduce this with hardness mapping. I use figures hardness 10 in this case. So this is a smaller section out of this of the same turbine disk. It's a quite complex figure. So the background is a macro edge image. The red lines, I just tried to redraw the grain flow for better visualization. And then on top of this, we see this color map, which is a hardness map. So from blue to red, just from low hardness to high hardness. If we just look at the macro etched images, we find there's some elongated grain flow in the high hardness region and this curved grain flow in the low hardness region. Now, if we take these samples into the light optical microscope, we see that the low hardness region also has this larger grain size. Here is some areas with larger grains. If we take it again into the electron microscope and do some EBSD, we can confirm that finding where we have a larger grain size. However, this grain size difference is not enough to account for the observed differences in the strengths. So there must be more going on. If you look at the delta phase fraction, it's already low because these are directly aged turbine disks. But in the low hardness regions, we find even lower delta phase fractions. If you look at these bright platelets again. And in addition to this, we can also plot our geometrically necessary dislocations again, and we find that these larger grains contain much less dislocations. Okay. The next step, we did some chemistry analysis. The top is the specification for this alloy. Then we have some inductively coupled plasma, AES. On the bottom side, we see our Atomprobe results. So with the AES results, there's nearly no difference between them. So there's no significant chemical segregation going on, although the Atomprobe shows some slight differences, but again, it's a very highly localized technique. If we now go to a bit higher resolution techniques, we can use the SEM, set it up very carefully and find the precipitate structures, but it's easier with the TEM to find any differences, because we do see here in the bright field as well as in the dark field that there seems to be a lower lower density of these precipitates in the low hardness region, whereas the precipitates in the high hardness region are quite densely arranged. And we can take the same material and put it in the Atomprobe. On the top part, we see the high hardness region. We can apply our toolbox with these methods and find that the particles are overall smaller with a higher density. So that fits very well what we have observed in the TM, but they also have a simpler morphology. So we find less of these triplets, but more duplets. Whereas in the low hardness region on the bottom, we find a larger particle, less densely arranged, and more in a triplet morphology. And considering the particle size and density, these are very important indicators that could explain the lower strength. Now, if we compare these actually as plots, we find that the volume fraction and radius are small differences, but especially the particle density has a major change here. Okay, and here we have the plot of the different morphologies as a summary. Now we can go back to our microstructure model and adapt this for the situation in directly aged turbine disks, where we start again with this gamma matrix with a lot of dislocations and a little delta phase on the grain boundaries. And these turbine disks are really complex, so that the local temperature and the local strain that are induced can vary significantly. And in this case, the high hardness region experienced a moderate temperature as well as a moderate strain. So that not much has changed in this case. We retain the high dislocation density and the delta phase volume fraction, which is in favor of a very fine distribution of our precipitates. I call this a stable direct aging in this case. Now our low hardness regions correlate with a high temperature and high strain. And what this can do is actually dissolve some of the delta phase, which would result in a lower volume fraction. But if the delta phase is dissolved, this means we have more niobium in solid solution and less dislocations as well. So we have this grain growth occurring, more niobium, less dislocations. And that's in favor of more widely spread precipitation. I call this unstable direct aging for the reason that there's less nucleation sites and the growth is very much accelerated due to more niobium. All right. Now to the last chapter, where we can use all this knowledge we have acquired before to study the early stages of precipitation during direct aging in this alloy. And the motivation behind this is that we have observed these co-precipitates, gamma prime and gamma double prime, but we don't know which one of these precipitates occurs first, or maybe they occur simultaneously. We also don't know how these duplets and triplets form. Maybe they form at the same time, they grow together, or another particle forms on top of a first particle. So that's all questions we would like to get some insights here. And in our approach, we took the same material from an industrial forged, not disc, but an industrially forged material that has been air-cooled, and then created an interrupted direct aging sample stream. You see, this is again our time temperature profile. The solution annealing is gone, your direct aging, and each of these black arrows marks one sample. And what we can do with these samples once we have heat treated them is do some hardness testing. As you see here, over the direct aging time, we see the hardness profile roughly fits to an exponential growth function. We do see there some outliers here after 2 hours, then in the transition, as well as in the aging too. But to really understand how these initial stages of the precipitates form, we selected these samples highlighted by the black arrows. So the as forged, 0.2 hours, 0.6 hours, direct aged, and then fully aged. Then we can take these samples into the TEM, and if we look at the as forged material, that's figures A and B, we see there's a lot of small precipitates and a few larger ones. Now that's not unexpected because the material has been air cooled, so there might be already some particles forming during the cooling process. After 0.2 hours direct aging, these small precipitates haven't changed that much, but we do see that these larger structures grow quite quickly. After 0.6 hours aging, we find that these larger structures have grown a lot, but also the smaller particles now start to grow. So that after the fully aging in figure G and H, you have this typical microstructure of these really densely arranged precipitates. We can also take these samples into the high resolution TM. We did this only for the as forged condition as well as for the 0.6 hours direct age condition. And what's pretty great with the high resolution TM is we can show that these are indeed precipitates. What's relatively easy to show is gamma double prime. Gamma prime you can see as this slightly darker region. I hope this comes through Zoom all right. Nonetheless, we can do a fast Fourier transform. That's this top inset, and we do see there some superlattice peaks, which show us the presence of precipitates, as well as the brightness profile shows us some ordering too. The situation is quite similar after 0.6 hours direct aging, except that these superlattice spots and the ordering in the profile become stronger. While we have these samples in the TM, we can also do some TM EDS. In the as forged condition, there's very little segregation occurring. What we see at all are some indications of nickel and niobium along these coarser structures. And after 0.6 hours direct aging, that's 36 minutes, we see quite clear segregation along these coarse structures, as well as along these smaller particles. But to actually quantify these precipitates, you have to go back to the Atomprobe and calibrate all these data sets. So here we have smaller data sets as acquired in the voltage mode, right? We need to know our well-calibrated particle shape first, before we then can actually calibrate large-scale data sets. But these are large enough to get some precipitate size descriptors so that we can calibrate our large-scale data, as you can see here. And indeed, in the S-forged condition, we have a high density of small particles, which looks very similar after the 0.2 hours direct aging condition. We're lucky here in this data set, we captured one of these larger structures, which together with the high resolution TM, we could show are large gamma double prime particles. After 0.6 hours direct aging, these particles start to grow. And then we have this typical microstructure in the fully aged condition. All right, and now we can analyze each of these steps in terms of volume fraction, which follows a nearly linear function. We can have a look at the particle radius for the small population of these particles, which remains almost constant until 0.2 hours direct aging, and after 0.6 hours, we see these particles start to grow. If we look at the number density, we can confirm that the first 12 minutes are the nucleation regime, followed by the growth regime. We also see that we start with predominantly monolithic and duplet particles, which then, well, the duplets are increased in the fraction, and then the monoliths transform into the triplets. While we have this Atomprobe data, we can also extract the chemical composition of these particles, and we see in figure E, gamma prime is enriching over time with nickel and aluminum and titanium. Now that's expected, but if you look at gamma double prime, it's doing something interesting, where it's enriching in nickel and niobium, but it's also rejecting aluminum and titanium back into the matrix. We can have a look at the shape of these particles. So if we plot them for each aging step, we see they do start as near spherical particles, which then develop into these disks. So this is a comparative plot on the right-hand side with some other studies, mostly based on TM, but we can separate our gamma prime and gamma double prime into small particles, which fit very nicely into this previously observed trend. And then our coarse gamma double prime structures, they do not fit, which is an indication that these particles are already coarsening and therefore have lost their coherency to the matrix. And that's really important for this phase, because once gamma double prime has lost coherency, the contribution to the yield strength is very low. Okay. Now we can adapt our microstructural model even further. We start with the air cooling after the forging, where along these dislocations, we have a high attraction of niobium, whereas aluminum and titanium, in this study, we have not observed a similar trend. Okay, so at least for niobium, the diffusivity along dislocations seems to be greatly accelerated. What this means is we have this gamma double prime particles forming along the dislocations and then growing quite rapidly, whereas the population of smaller particles, they grow much slower within the matrix. After 36 minutes of aging, all populations start growing, and during the time of 0.6 hours direct aging until the final aging step, we observe this formation of co-precipitates. If we consider the change of the chemistry, we see that gamma double prime takes niobium from the matrix, but gives back aluminum and titanium. And this favors the precipitation of gamma prime on the interface of the gamma double prime particles. Whereas for the gamma prime particles down here, we have the opposite case. So aluminum and titanium are taken from the matrix, which favors the precipitation of gamma double prime precipitation, so that in the final microstructure we end up with these co-precipitates. All right, now let me move on to the summary, just to wrap up what we have observed. In the first study, we have observed the interaction between the delta phase and gamma double prime precipitates through the niobium concentration. We also have observed that the dislocation density plays a very important role. With our Atomprobe microscopy toolbox, we could find ways to calibrate large data sets and quantify our co-precipitate morphologies, which we then can use to quantify data in turbine disks. These are incredibly complex because we have a lot of factors during the manufacturing in the microstructural playing together. But we can also quantify our early stages of precipitation, where we have observed homogeneous and heterogeneous nucleation. And we found that the secondary nucleation is favored by the change of the local chemistry. So there's been my work in our group. We're actually having some continuing projects on this. For example, on the left-hand side, PhD candidate Peter Rielli is comparing different cooling regimes on the early stages of precipitation. That's been published. You can find that in this paper. And then we also already had a look at the delta phase matrix interface, which is a bit site-specific preparation here. That's also another paper that's out there. Last but not least, I want to thank Microscopy Australia, of course, our friends at Sydney Uni, and our industry partner, First Alpina. They need to be acknowledged as well for their expertise and the material they provided. I thank you for your attention, of course, and I'm happy to take any questions.
Okay, thank you, Dr. Felix Teska, for the informative and interesting talks. Now we have about maybe 15 minutes, or yeah, at least 15 minutes for the discussion session. Now you can, for the participants, you can ask directly to Dr. Felix Teska, or you can also write on the chat tab. But now we have one long question from Mr. Halashon Simanjuntak. Maybe Mr. Halashon Simanjuntak can ask directly to Dr. Felix Teska, because the question is very long, I think.
Yeah. First of all, I want to introduce myself. My name is Halashon, but you can call me Hans.
Mr. Halashon, your sound is unclear.
Hello.
Hello, hello. Okay, okay.
My voice is clear. Hello.
Hello, hello. Can you increase your volume?
Hello.
Hello. Okay, okay, okay. It's clear now.
Hi, Felix. Introduce myself is Halashon, but you can call me Hans from SKF. My question is it material?
I think the sound is, the voice is not clear.
Hard to hear it. Yeah.
Hello.
Hello, hello.
Hello.
Hello. Yes, yes, yes.
Is it clear?
A little.
Is it clear enough? Because already yelling and screaming.
Okay, okay. Or maybe I can.
Yeah, maybe you can read. Maybe you can
just read out the question.
Okay. Maybe I can just read the question.
Because maybe the connection or something.
Okay, okay, okay. So the question is it material Nicrofer 5219 Super MV and so on are the same from perspective chemical composition and specification, even if all above using 7118?
Right.
And another question is, what is the strongest material, titanium alloy or superalloy 17718? Because if I had no mistakes, both application material applied at aerospace or aircraft. Maybe you can ask. Maybe you can answer this question first.
Yeah. So the first question I think is about It's about this Udimet and Haynes, is that right? So these are different grades.
Yeah. Kind of the material. The name material is Necrover 5218, Supreme
Yeah.
718, Highness 718, Pyramid 718, Superhammer 718, and Udimet 718. They are the same from perspective.
So they can change slightly depending on the manufacturer. I'm only aware of Inconel 718, and then our project partner, which have
all about using 7.8.
Oh, yeah. So you have to look after the specifications, because what we worked with is alloy 718, which is where it's specified as this alloy. But there's also Inconel. I think the overall chemistry shouldn't change too much, but there's been some studies on the alloy chemistry which can have quite dramatic influences on the precipitation. So these results pretty much apply to this alloy composition, which is so that's the one according to our specifications here, right? Okay, I think the other question was about titanium.
Titanium and superalloy 718.
Yeah. Okay.
Which one is the strongest?
It all depends where you want to use it, right? Let me pull up this jet engine here. So each of these sections have their own demands, right? So titanium, for example, has the big advantage. It's very strong and very light. So you would use it in the compressor sections. But as soon as you go up to these high temperatures, like 600 degrees centigrade and above, you have problems with titanium. So then you need to go to these superalloy grades, which are high temperature resistant, like they keep the strength for up to 600, 800 degrees, but they're very heavy. And that's, again, a penalty for the fuel efficiency.
Okay, so it depends on the specific application, right?
Yeah, you need to look where the material is used in the jet engine.
Okay, maybe we have another question from Mr. Afandi. Mr. Afandi, you can.
Hello, Mr. Felix.
Hi.
Good morning. So I have a few questions regarding this volume fraction. Actually, I was about to ask you what is the volume fraction between this L12 structure and then DO22. And then the last few slides, you saw me that after heat treatment, let's say after early stage and then after 10 hours, the volume fraction changed quite considerably, in which the volume fraction of DO22 is much larger. So does it mean if you prolong this material for long heat treatment, like 1000 hours in service, the volume fraction will change also, like DO22 is much higher than L12 structure? So does it mean that DO22 is more stable than L12 structure? So the second question, I would like to know if there is the mechanism of the transition from L12 structure to DO22. So there is some transition of the structure from L12 to DO22. That is the second question. And then the last, maybe the atomic composition of the niobium is quite small. And then how we can have this much DO22 volume fraction? So if you, let's say, remove this niobium, like half or even totally remove niobium, what will it be the mechanical properties of this material? So you can only have L12 structure without any DO22 or DOA delta phase, which is, I saw from the presentation, the main constitution is niobium. Okay, that's all. Thank you so much.
Sure. Please remind me if I miss any part of the questions. So the first one is the stability of the DO22, which is the gamma double prime.
Yes.
Gamma double prime.
And that's actually less stable than the L12. It provides a lot of strength for temperatures, I'd say up to 650, 700 degrees centigrade. But above this, you get a transformation of gamma double prime into the delta phase. So any strengthening effect is completely lost. That's the big disadvantage of this alloy 718, that you cannot use it at much higher temperatures than this. So these really high temperature resistant superalloys, like up to 1000, they all use gamma prime, which is L12 ordered. Then you had a question about the low fraction of niobium. If you look at the composition of the gamma double prime, it's a nickel 3 niobium, which is 3/4 of this is just nickel, so you don't need that much niobium actually in there. If you remove it up completely, though, you wouldn't really get. You have a different alloy, right? You wouldn't get the delta phase. You wouldn't get the gamma double prime, of course. You might get different phases, though. Like if you change the equilibria, that can have a large impact. I think the alloy 718 plus was an approach to try to make a variant without gamma double prime, but I'm not sure how far research has come about this. There's been a couple of publications a few years ago.
Okay, so maybe you missed something, like in this figure, after 10 hours, the volume fraction of the gamma double prime is much larger. So if you prolong this for long hours, let's say 1000, do you think that gamma double prime will have more volume fraction than this, or there is some equilibrium state in which there's no change between the gamma prime and gamma double prime volume fraction?
At up to 650, up to 650 degrees, it should be stable. But for very long-term exposure, we haven't done any experiments, right? Okay. But it might be that some TCP or Larves phases are forming them. That's been reported in some long-term exposure studies. But yeah.
Okay.
That would be something to explore for sure.
Okay. Yeah, I think it's enough. Thank you.
Okay.
Thank you.
Okay, ladies and gentlemen, if you have other question, please just ask directly to Dr. Felix Teska, or you can also write on the chat tab in this Zoom. Is there any other question? So in general, Felix, I want to ask you, which one is more accurate for identifying the element between you display the atomic probe microscopy, and how about the EDX from TEM? Which one is more accurate?
Both are accurate, right? But Atomprobe has this really high noise to signal ratio, so we can quantify very low amounts of these alloying elements. For example, here, I'm able to identify these particles in the S-Forge condition, whereas if we look at the TEM EDX, we don't get a very clear signal here. But if we have any larger structures, then both become feasible. Yeah.
So in this term, the atomic probe microscopy is better, right, than EDX from TM?
for very small structures, very light elements, yeah, and because you can quantify basically any element up to hydrogen. Hydrogen is difficult, but that has something to do with the vacuum system of the machine.
Okay, because we have no atomic probe microscopy, I think, in Indonesia, so it's very interesting. Okay.
Elaborate.
Okay.
Elaborate, yeah.
Okay. If there is no other question, thank you.
Dr. Wahyu.
Okay.
That's a very short question because I'm really curious with your result by using TEM. You saw us at the slide number 33. Could you show to us again?
33.
Yes, yeah.
Yes. Yes. You mentioned that that is a high resolution TM image, right? And then you can get also the atomic, right, in the nanoscale structure. So I just curious, you set the G factor by the TM, right? In this case, the direction of the diffraction patterns in the B and D for the W gamma prime, is it? Shows that the difference between X4 and direct H in very short time, only 0.6 hours. But if you also see the precipitations, the dislocation density, actually in the next slide, perhaps the structure also similar. It is mean that the direct agings, because of the very short times, or what else? And how can you prepare that samples? I mean, I just worried that if you prepare by the FIB, there is some contamination that will be affected to the precipitation in your structure.
Yes. So maybe I start with the sample preparation, because that was one of our concerns too. And all these, all Atomprobe samples, all TEM samples have been electropolished. So you would grind a very thin foil, make it a disc, and then electropolish it. So you have no contamination from the fib and no deformation from any grinding steps left over. The challenge is getting samples suitable for this high resolution TM. Took me a bunch of attempts to get a very, very thin sample. So you need a couple of attempts to get good enough samples. The first question, I think I missed the first part of your first question. That's the...
Because I saw that the structure is quite similar, right? As the fourth and direct H only in 0.6 hours. Is that because of the very short times? Because the G factor, if we see in the diffraction pattern in the figure B and D, this is also similar.
Yes. So what we can show here is that we indeed have already precipitates in the as-forged condition, which then grow very quickly. Because if we just look at the Atomprobe, it might be just some accumulation of niobium. It might not be ordered, which would be a precipitate. But here we can show they are already ordered like they are later, after 0.6 hours. Yeah, which makes them precipitating particles.
Okay, I see. Okay, Dr. Wahyu, thank you, Felix.
Thank you.
This is very interesting research work. Yes, and the data also is very, very wonderful. It's a very, very challenging research. I know it. Wow, congratulations for your work. That's very great.
Thanks for having me.
Okay. Is there any other question from the audience? So if there is no other question, thank you, Dr. Felix, for your wonderful presentation. And we hope we can collaborate more, particularly with researcher from Research Center for Physics. And for the next presenter, we have Mr. Bravola, Mr. Bravola A Bancin from Thermic Coating Industries. He will present about HVOF coating application on turbine blades. For Mr. Bravola, you have about maybe 30 minutes for presenting your works, and time is yours now.
Okay, thank you, Mr. Wahyu. Greeting for all of us for this afternoon. I hope we are healthy and blessed. Okay, I would like to present about HVOF on turbine blades. I will share the, before it, I would like to know if my voice is clear enough. Please confirm.
Yes, clear enough.
Okay. Okay, we can look the presentation. Is it? Can you see it?
Yes.
Okay. Thank you for your time, Mr. Wahyu. I hope this presentation will be useful for industries in Indonesia, especially, or maybe for international. Okay, let me start my presentation. HVOF on turbine blades. What is HVOF? HVOF is one of process from surface engineering that's called thermal spraying coating. Thermal spraying coating, maybe some us is familiar about it. Thermal spray coating, there is many methods, and one of the methods is called high velocity oxygen fuel. And then what is thermal spraying? Thermal spraying is a group of coating processes in which material are deposited into a variety component. This is the material, the feedstock. The form is can wire, powder, or rod, and the type material can be ceramics, metal, and alloys, carbides, and many and others. And then the material is got heated by electrical or by combustion, and then the gas will spray the melted material to some surface, the surface to be coated. That's the principle of thermal spraying. And the thermal spraying, this is the microstructure examples of thermal spraying process. That is called process, virtually no heat input to the substrate, mechanical bonding process. It's just mechanical, not metallurgical like welding. And we can spray many materials, and the thickness is typically 100 to 750 microns, but can be more. Okay, this is thermal spray coating comparison. From comparison with many coating process like PVD, CVD, hard chromium plate. Yeah, the typical coating is about up to 3 millimeters, and the coating material can ceramics and metallic alloys. The characteristic is for wear resistant, corrosion resistant, and common application is for bearings. Yeah, this is the thermal spray coating advantage that provide resistance. Thermal spray coating can provide resistance to wear, erosion, cavitation, corrosion against corrosion under insulation, and abrasion or heat, and many more that can extend the life of new components. This process is coating the material so it can improve or restores the worn component like this blade. We can extend the life of the display. Thermal spray coating is a process that comply with BOD, Green Procurement Policy, that there is no hexavalent chrome, no cadmium, no phosphate, no halogens, no toxic component from thermal spray coating. So this is sometimes become the alternative from chrome plating that produce hexavalent chromium. We can see this is a thermal spray coating booth. This is a robot, arm robot to help spray process. And we can see this is women. What we think is this is women in engineering workshop. That means this process, the thermal spray, is safe. Even a woman can do it. Not only men, strong men maybe, but women with enough training and learning can do the thermal spray coating. So this is safe if the booth specific can complete provide. Yeah, this is thermal spray coating classification. The heating process can be by combustion or can by arc, by electricity. And HVOF is process that need heating from combustion, from gas. And we, Thermic Coating Industries, using propane and oxygen for the heating the material. Yeah, this is the HVOF coating. HVOF, what is HVOF? HVOF is high velocity oxygen fuel. We can see this is the principle of process HVOF. Oxygen, fuel gas. HVOF can be liquid gas or gas. If in our workshop we use propane in the form of gas. And the spray motion, HVOF, high velocity oxygen fuel, is very supersonic speed. In the motion, that can be formed diamond shock waves because the resonance of speed spraying to the component, to the workpiece. This is a kind of fit material for HVOF using powder, very, very fine powder. Okay, this is some materials that can be applied by HVOF coating. We can see here nickel-based superalloy powder that can be similar to alloy Inconel and Inconel 625, Inconel 718, and similar to Rene 80. The powder size is typically around 5 to 600 micrometers with morphology spheroidal. And then the other materials is tungsten carbide. From carbide, these two kinds of material is common use in our workshop. This is very common to be applied in to our customer parts. And then another HVOF material is silicon carbide. Even stainless 316 we can apply it with HVOF coating. And this is the function or the target of the coating, what is used for. This is HVOF coating characterization, comparison with another process like combustion powder, HVOF, electric arc, and plasma. We can see here that gas temperature, plasma is the highest. HVOF is around 2,600 until 3,000 Celsius. And this is the spray rate. The powder deposited to the substrate, and the particle velocity it's up to 700 meter per second. It's more than sound speed. And the bond strength, the HVOF is the highest comparison with this for process. the highest. If for ferrous alloy, non-ferrous alloy, it is the highest. The coating thickness typically, if HVOF, it's up to 2.5 millimeters, but sometimes we just apply the HVOF in our workshop is up to 500 microns because it is enough for the parts component. And the hardness for ferrous alloys with similar or same material, the HVOF is produced highest hardness compared to electric arc, plasma, and combustion powder, because the kinetic energy from the impact from the powder to the substrate, the impact energy, because the speed is supersonic, so it increases the hardness of the part, more dense and harder. The porosity is the lowest, the HVOF from other process. So what is HVOF coating advantages? It's higher density, lower porosity because the kinetic energy from the impact of the powder to the substrate. We can see this is the flame test before the coating is conducted. We can see here like diamond because it is very fast. And then higher strength bond to the underlying substrate to improve the cohesive strength within the coating. Lower oxide content due to less in-flight exposure time, because the powder from the gun to the substrate is in short time, so the heated powder don't have time to oxide it. Smoother sprayed surface, higher hardness due to less degradation of carbide phases. Improve corrosion protection due to less true thickness porosity. And then what is this disadvantage of the HVOF coating? It is HVOF equipment requires more investment than other thermal spraying process. For example, flame and up spraying. HVOF spraying requires experienced qualified personnel to ensure safe operation because it's heat very hot, so it needs safe condition environment. HVOF spraying usually needs to be undertaken in a specialized thermal spray booth with suitable sound attenuation and dust extraction facilities. The sound is like jet combustion is very disturbing. So it needs a specialized thermal spray booth that requires more cost, more investment. And then powder size are restricted to a range about 5 to 60 micrometers. Yeah, because with this size, it's appropriate it's appropriate to the heat the material to surface. Okay, this is the HVOF coating process. Brief. First, we do pre-inspection. This is turbine blade from coal-fired boiler. The function is to extract the dust from the boiler, and we can see this is the blade is almost wear. This is very damaged. We do the pre-inspection. First, we do the pre-inspection, perform visual inspection, and then hardness, non-destructive test, and etc. of the parts. And then we do surface preparation. The surface preparation is very mandatory. We use the sandblasting, aluminum oxide. It's for cleaning and roughing the surface. And the minimum requirement for the clean liners is 2.5 to three clean liners. It means no dust, no contaminant, and ready to be coated. And then the process of HVOF coating, set the correct parameters like gas flow, spraying distance, etc. Depending on the powder will be coated to the blade or to the parts, and then final inspection. Yeah, HVOF coating on turbine blades. Almost 50% of the turbine blades failures are related to fatigue, stress corrosion cracking, and corrosion fatigue. Once a crack is initiated on the blade surface, it grows rapidly and causes blade failure. Then it needs to be coated to improve or extend the life of the blade. Then why must HVOF? HVOF produce a coating with higher bond quality, higher hardness, lower porosity, and way better corrosion resistance. The coated turbine material like superalloys give more corrosion resistance and reduce the degradation. Yeah, we see before that from the table that HVOF is better than another process for the blades. Then here is coating facilities in our workshop. We have the HVOF machine, and then we have the ABB IRB arm robot. We often use this robot to help the spraying so it can be stable. So the spray quality is good enough. And this is the example of coating blades with HVOF and robot, HVOF robot. You can see here it's blade and coated. Okay, this is the picture before. We do the coating, repair and coating for rotary fan coil steam turbine. This is before. This is HVOF coating process. We can see here it is very damaged because the fly ash content of silica compound, and the silica is impact the blades. And then we rebuild it, and then we do the HVOF coating process. After the HVOF coating process, we do the dynamic balancing. This is mandatory because this is rotary components, and they are need dynamic balancing. And this is finished. And we ever do the training and supervision for the same part in Vietnam. We collaborate with FIFA Blast. Yeah, okay. This is another turbine components from industrial gas turbine. We do the repair for the bearing and seal areas. Yeah. We do the repair for this bearing. The customer don't want to put the blade because they prefer to replace the blade than to coating the blade. Yeah, so we just do the repair for the bearing and seal area. Okay, and there is another application of HVOF coating, not only to turbine blades, but it can apply to sleeves, bearings, piston compressor, shaft pump, shaft mandrel, rotors, and ball valve. This is our specialization in our workshop is ball valve. We have the CNC machine to make sure the roundness of the ball valve is perfect. Yeah. And another application is HVOF can be applied to wall tubes boiler. One of the most significant issues in boiler operation is erosion damage. So HVOF sprayed with nickel chromium carbide is one of the most important candidates for protection of the material from high temperature erosion. Increase wall tubes boiler component, and the material is good adhesive between the coating and the substrate, resistant to corrosion and erosion. the materials is depend on the environment specification. Okay, this is another thermal spray coating application. Is can be applied in HVOF coating gate valve. And the thermal spray coating commonly is can apply to TSA, thermal spray aluminum, to storage tank, pipe, vessel tank, and it corrosion protection and against corrosion under isolation. This is on-site application of TSA. Is another TSA process. Yeah, this is TSA process 2 on pressure vessel 452 units mobile Cepu, Bojonegoro. This is carbide coating on shaft and housing using HVOF method. This is ceramic coating for carbon tray. Sorry, this is ceramic coating for carbon tray that can improve, extend the lifetime of this carbon tray, because sometimes the part produced is sticky to this carbon, and it abradable, and the product is abradable. And then this is another process we do, that's ceramic tough coating. This is ceramic composite coating. Ceramic composite coating applied on wall tube boiler. Yeah, this is another application on superheaters and wall tubes. And this is a thermal spray coating application. Another thermal spray coating application can be applied on crankshafts, stationary blades, heavy industry part, HVOF coating on shaft, ceramic coating on exhaust manifold. And this is the part of heavy industry equipment, and helping by retainer with ABB arm robot. Yeah, we can cooperate to improve durability and reliability. We can apply on rotor turbines, blade, ball valve, sleeve bushing, rolls and screw, wall tube boilers, high define and ducting, and many more. Okay, thank you. That is maybe my presentation to be shared to all of us, that we are the applicant from Thermic Coating Industries, do coating for turbine blades and other parts too. And maybe this is the knowledge I can share, and I would like happy if there are any question to be discussed. Thank you. Maybe the time I give back to Mr. Wahyu.
Okay, thank you, Mr. Braviola, for the interesting talks. And now we have about 15 minutes for the discussion. And I see from the chat there is already question from Mr. Halason. Maybe you can ask directly, Mr. Halason.
Hello.
Yes.
Hello. Is it my voice okay?
Okay. Okay, maybe I can help you by reading the question, because your voice is not clear. Can I?
Yes. Okay.
Okay. So here the question is, we can conclude that coating type can increase all characteristics, as example hardness, density, etc. Am I right? And may
Yes.
I know how many times this has been done and in which turbine?
Okay, I will ask the question from
Mr. Halason.
From Mr. Halason, Horace. Mr. Halason.
Hello.
Yeah. Yes. Sorry, the voice is not clear. Yes, the process as can increase all the characteristic of example of the components like hardness, density, and etc. It's depend on the material applied on the components. And may I know how many times this has been done and which turbine? We have do around 8 times for the steam turbine in coal-fired boiler. Yeah, like the presentation I present before. We do this is almost 8 times, as I remember, or could be more. Yeah, for this turbine especially. But our team in Singapore ever do the coating in industrial gas turbine. So Thermic is group of companies in Singapore and in Indonesia and in Taiwan. And our specialization in Indonesia is in ball valve and this turbine blades for coal-fired boiler application. This application is to sucking the gas from the boiler. So it gets damaged because the dust is content of particles that harmful to the blades. Maybe it's enough or anything else, Mr. Halason?
How long you take the process of coating in one turbine?
Excuse me, Mr. Halason, your voice is not clear. Can you repeat your question?
How long you take the process coating in one turbine?
Okay.
Maybe I'm stop my camera, yeah. So the connection can stable.
Okay, I think I get your question. How long the process is conduct? For new parts, we can do it for around a week for new part. But for the damaged part, we must pre-inspection first. What the damage of the turbine, and then we have to analyze it, and then we can sure how long it will be take until the final inspection. But for new parts, it took around 5 days or a week. That is Mr. Halasan.
5 weeks.
Yeah, a week until the HVOF coating. But there is another requirements that the rotary part is need to be dynamic balancing, and it is in outside of our control, but it could take a week. So the total until finish or until it can be used around 2 weeks for new parts. But from our experience, from 8 parts of ID fan or from 8 parts of rotary fan coil, all of them are damaged, and we have to rebuild it, and it took a month.
Yeah. Oh, I see. So how many warranty? You give a warranty, right, for the coating, right?
The warranty for new parts is 1 year, but for the repair parts is 8 months.
Oh, 8 months. Okay, got your point. Thank you, Pak. Thank you, Pak.
Thank you, Mr. Halason.
So if there is a cases, you can record the part, right?
Yes, of course.
Okay, before 1 year. Okay. Is there another question from the audience? Okay, if there is no question.
Dr. Wahyu.
Okay. Dr. Eni, please.
Hello.
Hello.
Okay. Hello.
Yeah, I think your signal is unstable.
Oh, regretful. Hello, is it okay?
Yes, yes. Maybe you can turn off your video.
Mr. Bravo.
Yes, Miss Annie.
Okay. You have already presented several techniques for the thermal spray, and the interesting is that for the hard, that's appropriate for only the metallic, right? And then the shape of the particle or the powder, the coating material is should be spherical. So for example, if we are from our lab, we try to mixture the coatings materials. It means that not commercial products, not commercial powder. So it means that sometimes if we use the ball milling, the powder particle looks like flakes.
Yeah.
So if the particle size is not more than 60 micrometer, is it safe for the HVOF gun to deposit our coating materials? Hello?
Okay, hello.
Okay.
Okay, I'll try to answer. This is the recommendation of the HVOF coating. That's the morphology should be spheroidal. If there is another morphology like flakes, it will damage the HVOF gun and then the hoses faster, and the burning or the heating of the material will be not similar in all its maybe, but in spheroidal the heating is efficient.
Okay.
Mm-hmm.
So in other words, the spheroidal shape is a must, right?
Yeah.
Okay.
But if the powder production is just can be in flake morphology, there is another option that.
Tolong jangan video dong, Bunda sinyalnya lobet, jangan streaming.
Okay, but if there is a flake morphology, there is another option that we can use arc spray process. Okay, from electrical electrical combustion. The powder is covered by steel to form a wire. So the heating material is from this process.
Okay.
Yeah.
So for non-spheroidal shape, we can use arc plasma spray, right?
Yeah, for non spheroidal, but it must form to wire form.
Oh, not in
cannot powder because
okay.
powder is only for HVOF.
HVOF. Okay.
Yeah. Plasma combustion flame spray.
Okay.
Like that.
But how about the comparison of the performance?
Sorry?
How about the comparison of the performance between HVOF
the comparison
and
of the performance? Here, maybe I can share again. Okay, Mr. Wahyu can see the table. Okay. It says from the table the sources of this data from our Recon data, or Recon Medco, and some references. It says HVOF produce highest bond strength. Okay, I can share it. Highest bond strength from another process. But sometimes in aerospace application, they are use plasma, not HVOF, because plasma can heat the material up to 12,000 Celsius, and it will make sure the material is melted enough, like that.
Okay. Okay. Is there any other question from the audience for Mr. Braviola? From Mr. Bravola, sorry. Okay, if there is no other question, I think thank you for Mr. Bravola for the interesting talks. And after this, we will have the presentation from Dr. Annie.
Okay.
Dr. Annie, are you ready now?
Maybe I will give the closing statement.
Oh, okay, okay.
Okay,
Please.
thank you. Thank you, Mr. Wahyu. I'm sorry for the inconvenience that I late to join this webinar because of technical issue. Yeah, but I hope this presentation can be useful for us. Actually, for the researcher, sometimes we order all the parts is from the foreign country. Yeah, maybe it's challenging for us in Indonesia to make the machine, to make the material, okay, from so we can, yeah, we can just proud to apply our product,
Okay.
our own product. That's maybe okay. Thank you for all participants. Yeah, thank you.
Okay, thank you, Mr. Bravola, for your interesting talks. And now we have our last presenter, but not least, I think. Dr. Annie, are you ready?
Yes, Mr. Moderator.
Okay.
Okay, let me share screen first, my presentations.
Okay, Dr. Annie, you have about 30 minutes for presenting your works, and after that we will have the last discussion session, and after that maybe all of you can do the photo session. So Dr. Annie, the time is yours now. Dr. Annie?
To apologize because, yes, can you hear my voice?
Okay.
Hello?
Okay, hello. It's already.
Is it clear?
Yeah.
Okay. Okay, first of all, let me introduce myself. I'm Sugiarti as the head of material research group. Today, I would like to present some part of my research work regarding the topic of this webinar. The title is Development of High Temperature Oxidation Resistance of Nickel-based superalloy for industrial gas turbine. So for the motivation,
Hello, Dr. Annie. I think the signal is unstable. Hello, Dr. Annie. She just left. Okay.
I'm really sorry for the unstable connection. Okay, let me try again to share.
Yes, please.
Okay, I will continue it again. So, in addition, data obtained in 2019 shows that Indonesia is the first ranks of the world's largest exporter of coals by weight, and Australia, your country, Felix, in the second rank. So, unfortunately, the combustion of coals adds a significant amount of carbon dioxide to the atmosphere. Therefore, one of the solutions to solve this problem is by increasing the efficiency of energy productions with increasing the operating temperatures and pressure for the gas turbine. So, however, the utilizations of power plant system has not been without technical and environmental problems. The problems are related to the gas turbine oxidations when the material exposed to high temperatures in coal-fired power generation system. This figure shows the scale observed oxygens when operating at higher oxidations. It is known that nickel-based superalloy are amongst the primary material used as a component for a gas turbine engine, especially for turbine blades because of their excellent properties against creep and fatigue at high temperatures. However, nickel-based superalloy has poor high oxidations resistant at high temperatures. Therefore, a protective coating is required. This figure shows the material development from the beginning of 1950 to 2000 centuries, from stainless steel to novel thermal barrier coatings with reactive element additions. Development in these coatings become more important to increase the protective material. There are several methods for depositing thermal barrier coating technique, such as thermal spraying, physical vapor depositions, electron beam physical vapor depositions. However, in the present study, we utilized thermal spray for depositing thermal barrier coatings. This figure shows the schematic illustrations for the thermal barrier coating system. There are three primary coating layers in TBC system as shown in this video. Metals can be composed with the nickel and cobalt, and X can be added with the reactive element. It's a bond coat layer, approximately 200 micrometer thick, and can be pretend as a bonding and oxidation protections. Mainly alumina layer. As the second layer is thermally grown oxide, which grow from 0 to 10 micrometer and act as a diffusion barrier. Typically, yttria stabilizes zirconia, as the third layer is the ceramic top coat in the TBC system, around 300 micrometer to 1 millimeter in thickness, which act as a main thermal insulation layer. So this is very important to know the main function of each layer, because, for example, in the top coat ceramics layer, it should have a low thermal conductivity, high coefficient thermal expansion, extreme temperature gradient, and so on. And for the bond coat ceramic metallic layer, the material should be aluminum reservoir for forming protective alumina oxide scale, and that it can also become an interdiffusion with the superalloy and capable of a creep and plastic deformations. So this figure shows the flow diagram of the coating process. Nickel superalloys was polished 1000 and then blastings in order to enable data. Initially, additions as the bond coat material was deposited by using high velocity oxide field technique, and followed by the depositions of the ceramic yttria and the coated sample treated in tubular furnace with a heating rate of degrees C per minute in argon 2 hours, and followed by 1100 degrees C for 2 hours. All of the coating samples were oxidized in air with 3 different temperatures at 1000, 1050, and 1100 degrees C for 100 hours in a muffle furnace. So the observation will be carried out by using XRD for the phase analysis and the scanning electron microscopy equipped with the EDS for the microstructure analysis and composition analysis. So in the next slide, I will discuss the result in microstructural and isothermal oxidations. Resistance of nickel, chromium, aluminum with reactive element addition deposit by HVOF method. Initially, commercial powder of nickel, cobalt, chromium was used as a coating material for bond coat layer as shown in these figures. This nickel, cobalt, chromium, aluminum powder has typically spherical particles with a size of 14 to 35 micrometers. Hafnium dioxide as a reactive element for doping materials has a smooth, near spherical nature of the seed as shown in these figures. And the seed particle of hafnium has been mixed with the precursor materials using planetary ball mill for 3 hours. And the morphology and the size of spherical shape of precursor material was similar to that of the without additions of reactive element. Therefore, the structure of hafnium as a doping element is hardly to be observed by using SEM. TEM characterization has been utilized in order to understand the mixture and distribution of hafnium dioxide in the precursor material as presented in this figure. These figures show bright field TEM image of nickel, cobalt, chromium, aluminum with the hafnium additions. The bonding nickel, cobalt, chromium, hafnium can be observed. Hafnium doping randomly distributed and surrounded the major particle of the nickel, cobalt, chromium, aluminum. To understand the effect of different substrate on the structure, the microhardness properties of the coating, characterizations of the coating on the carbon steels, Superalloy, and nickel chromes was performed. And this figure shows the cross-sectional structures of nickel, cobalt, chromium, aluminum, yttria, and additions of hafniums. It thought that the coating thickness on the carbon steels, nickel, chrome, and the Superalloy measure of about 270 and 80 micrometers. The HVOF coatings show relatively dense, contains some unmelted particle, and also for a few pores included in the coatings. This figure shows the hardness of the coating on the substrate has been measured along the cross section for 3 points, and the hardness is average. The hardness data is compiled in this table and plot in these figures. This is about 300 plus superalloy substrate with the hardness of about 250 plus minus 40. Oxidation behavior of nickel, cobalt, chromium, ammonium, hafnium will be described. An oxidation test was carried out at 1000 degrees C for 200 hours. On heat-treated samples at different temperature, which is 1000 and 1100 degrees C with different nickel-based superalloy substrate, nickel, chrome, and the Superalloy. It shows that heat-treated samples at 1100 was more protective than at the 1000 degrees C for 200-hour oxidation time. Moreover, the performance of the coating layer on Superalloy substrate has the highest oxidation resistance. Based on the microstructure and the micro hardness subjected to higher temperature oxidations, 1200 degrees C. So this figure shows that the wedge gain of the sample oxidized at 1000 degrees C is slower than that of sample oxidized at 1200 degrees C. The oxidation kinetic of sample oxidized at 1000 degrees C follow parabolic rate laws. The oxide growth occurs by the diffusions of the oxygen to the coated layer at the initial growth rate of the coated samples, followed by a steady state of the alumina oxide scales. The wedge gain reached to 0.4, as you can see in this inset figure, after 100 hours. On the contrary, the oxidation kinetic of the samples oxidized at 1200 degrees C exhibit a linear increase in mass gain with increasing the oxidation times up to 15 hours, followed by the dense or mass loss indicated the spoliations of oxide scales and the less protective for the substrate. The maximum of the wedge loss was about -8 milligram per centimeter square. Therefore, it implies that the sample oxidized at 1000 degrees C provide significantly better protections against high temperature oxidations. As a result, sample oxidized at 1000 degrees C with further analysis by SEM in order to understand the microstructure and oxidation mechanism, it heat treated and oxidized samples. HRM technique also can be observed. Further, the figure also characterized by using the cross-sectional secondary electron of SEM image accompanied by the composition map of S-coated heat-treated air was established with an approximate thickness of 54 for the S-coated and heat-treated samples and 91 micrometer for the oxidized sample. In homogeneous ionosyte to form intermetallic oxide. Further, similar structure was developed at the coated samples and the heat-treated samples. A very thin, and the existence of the aluminum
Hello, Dr. Eni? Hello, yeah, okay. I
Is
think
it
your
been a long time?
yeah, no. Yeah, I think your signal is very unstable.
Yes, I'm really sorry for that. You
Okay,
missed
maybe
for several parts of my
no.
presentation.
I think you can continue from this part.
Okay, thank you, Dr. Wahyu. So, in contrast, a thick and porous structure with the large void was developed at sample oxidized at 1000 degrees C as shown in these figures. So high intensity of the oxygen Hello? High
Yeah, yeah.
intensity of the oxygens on the top layer reacted with the aluminum, cobalt, nickels, and the chromium element. Therefore, it may cause the formation of transient alumina phases with a complex structure from the initial stage up to 100 hours at 1000 degrees C. It is worth to notice that longer exposure time for the oxidation test is required to obtain a thin and stable oxide scale formations on the coated samples. Therefore, the characterizations on the oxide top surface of these coated samples was performed in order to understand the properties of oxide scales. A cross-sectional SEM microstructure of oxidized samples showing formations of doubles oxide scale on the top surface composed of an inner continuous alumina supported by an upper mixed oxide layer. A localized area, an oxidized coating shown in these figures. According to the EDS point analysis, the outermost oxide layer consists of alumina grains, nickel light mean the above described. I will summarize the result as follow. Nickel, cobalt, chromium, aluminum, yttria, and addition with the hafnium bond coat having a high hardness value, oxidation test, coating applied on high alloy substrates has better oxidation behavior. And the oxidation temperature at 1000 degrees C was appropriate for evaluating the bond coat layer against high temperature oxidations. Based on the summary and to confirm the previous result for the bond coat layer, a further coating was also prepared with the hafnium additions and compared with the other reactive element like cerium, as it can be explained in this slide. The cross-sectional structure before and after oxidations of nickel, chromium, aluminum bond coat with the reactive element shown in these figures. It shows that the coating system thickness measure of about 150 micrometers. The improvement of the structure in the bond coat layer from the previous research could be recognized as more denser, less porous, and relatively smooth compared with the previous HVOF samples. After the oxidations, the sample consists of 3 layers: secondary reaction zones, coating layer, and thermally because help to keep the other layer. And in order to clarify the TGO layer, the high magnification was selected from the selected area here. And in the nickel, chromium, aluminum, and with the addition of hafniums, looks similar structure. The chromium oxide is homogeneously deposited on the outer part of the TGO layer. On the contrary, in the nickel, chromium, aluminum with the cerium additions, alumina is eventually distributed on the top of the TGO layer. Thus, it seems to be more protected for high temperature oxidations. Therefore, we try to oxidize the samples for a temperature of 1000 degrees C for 100 hours. This shows the oxidation schematic. The mass gain increase gradually with the time, and from all the 3 samples, it follows the parabolic rate laws. So the result shows that nickel, chromium, aluminum, and with the hafnium additions show similar with the mass gain around 1.8 to 2 milligram per centimeter square. While the sample with the cerium additions has a high oxidation resistance with the mass change only 1 milligram centimeter per centimeter square. And this figure shows the XRD pattern of those 3 coating samples. The phases before the oxidations were identified to be a mixture of a delta alumina, alpha alumina, theta alumina, accompanied with the spinols, chromium oxide, and gamma prime nickel 3 aluminum. Nickel 3 aluminum in the samples promote the quick formations of the alpha alumina from delta to theta. So according to this result, it clarifies that the addition of ceriums in the nickel chromium aluminum can modify the oxide growth process, the sample more protective against high temperature oxidations. Therefore, we would like to continue deposit 8% of yttria stabilized zirconium ceramic coating as a top coat layer for developing excellent TBC system. This is the study to understand the effect of heat treatment on the porosity of ceramic top coat. So we try to heat treat it, the sample at temperatures of 1100 degrees C. As you can see in these figures, the porosity decreased as a result of the heat treatment. Therefore, the material seems to be more compact and improve the bonding strength in the interface. This figure shows the oxidation kinetic also, the TBCC which complete with the bond coat and the ceramic top coat. All coating samples reveal a parabolic oxidation behavior. So the wedge gains is varied during for the 100 hours, which is the addition of cerium has a lowest mass gain, which about 0.91 milligram per centimeter square. So it verified that nickel chromium aluminum with the cerium having a smaller increment in the mass gain compared with the other 2 samples. Therefore, the cerium addition is more effective for improvement of thermal cycling life. This figure shows cross-sectional structure of the coated sample before oxidations. The coated composed of the 2 layers, metallic bond coat and the ceramic top coat. The coated layer was established at approximately 450 for the ceramic top coat and around 100 to 200 micrometer for the metallic bond coat. The microstructure for the bond coat of the nickel chromium aluminum and the others reactive element additions shows that contain high porosity. Porosity was also observed to the bond coat and top coat interface, like here, which is not favorable due to the reducing the strength of the coating system. A TGO were not visible at the interface of all coat sample before the oxidation test. So according to this result, we also confirm the coated samples by using the EDS mapping analysis that with the hafnium and the additions of ceriums, less porosity and crack, good bonding interface. Therefore, the TBC system for the cerium additions could perform as a barrier for the oxygen reservoir. So this is the line analysis of the samples. So this ceramic layer contains 70 atomic percent of oxygen and 35 atomic percent of zirconiums. So according to the by using the phase is mostly composed of zirconium phase with tetragonal structure. It revealed that 8% yttria stabilized zirconia could withstand for the formation of zirconia phase with the tetragonal structures. So we try to enlarge the, as you can see in this figure, the layer can be consist of alpha alumina formed by the reactions of aluminum, chromium, and oxygen in the diffusion process during thermal treatment. So the mechanism of the TGO formation could be explained by, and is already published from the Guojiang in 2017. So it's simply for descriptions of this mechanism. At the beginning, precipitations of a layer. And we have known that the diffusion rate of the cerium is higher than the aluminum, is higher than the cerium dioxide. So the thin alumina will be formed continuously, as you can see in the top layer here, as in the some part of outermost alumina scales. And when thermal export for a long time, this appearance of the beta nickel ammonium precipitate occur and make decrease of the aluminum diffusions. So finally, a chromium dioxide from on the top of the continuous alumina scales, as you can see in these figures, and at the same time, the precipitations, the internal oxide of alumina occur underneath the TGO layer. So in order to clarify the oxidation's behavior, the TBC system will further evaluate it by increasing the exposure temperatures of 1000, 1015, and 1100 degrees C. This figure shows the oxidation's kinetic curve of the coated with the ceriums and yttria stabilized zirconia samples oxidate at 1000, 1050, and 1100 degrees C. The oxide growth occur by diffusions of oxygen to the coated layer if the samples follow the parabolic rate laws that occur only at the sample oxidate at 1000 degrees C. On the contrary, the oxidation kinetic of the sample oxidate at 1050 and 1100 degrees C. So a linear increase in mass followed by the breakaway oxidations, so as protective for the substrate. So if we calculate, if we measure the weight loss, it was about minus 10 milligram per centimeter square. Therefore, it implies that the sample oxidized at 1000 degrees C provide significantly better protections against high temperature oxidations. So microstructure, image of the bond coat to coat interface were evaluated after the oxidation test at the 1050 and 1100 degrees C. And the thickness of the metallic bond coat layer was above 110 micrometer, and the ceramic top coat was above 200. And for the oxides sample at 1000 degrees C reached to 400 micrometer. Spallation on the ceramic top coat will occur at the sample oxidized in 1050 and 1100 degrees C, and that the oxidation kinetic curve follow the breakaway oxidation or mass loss. So rumplings, continuous, and thin TGO, as you can see in these figures, is found only in the oxidate sample at 1000 degrees C. So the thickness of oxide scale has been measured and about 1 micrometer in TGO. So this is a very important for the TGO characteristic for this TBC system. Further, we also characterize the XRD and shows that all the coating sample, even though the oxidations has been carried at different temperatures, but it shows that again major composed with the tetragonal zirconium oxide phases. So as you can see, so the increment of the temperatures oxidations didn't transform to the cubic and monoclinic structure of these zirconium phases. So now I have already reached to the conclusion of my presentations. So according to the microstructure of the TBC system from the bond coat of the coating samples, it shows that the high density and thin TGO layer, while in the top coat of 8% yttria stabilized zirconia, having a very good bonding in the interface and the less porosity. And according for the phase identifications, that in the bond coat, the phase consists of the gamma prime, spinel structure, chromium oxide, and the metal stable alumina. For the top coat, there is only a single tetragonal structure of the zirconium dioxide. From the oxidation resistance, we can understand that the reactive element can improve the adherence in the interface between metallic and the ceramic, and also for the TGO layer. And the sample with the additions of cerium as the reactive element had the highest oxidation resistance in the TBC system. So for the temperature oxidations, as you have already known in the previous slide, so 3 variations of temperatures have been selected, and the result shows that 1000 degrees C showing a better and appropriate temperatures due to the formations of the TGO layer with a continuous dense and thin layer consisting of stable alpha alumina. This is the end of my presentations. So thank you very much for your kind attentions. So please give me your comment or questions, and I will give back to the Dr. Wahyu. Thank you.
Okay, thank you very much, Dr. Eni, for the nice and interesting presentation. In spite of the signal problem, I think the presentation is very, very good. But for further elaboration, maybe there is some question from the audience. Is there any question? Okay, maybe if there is no direct question, I will read the question from the audience in the chat. The question is there any effect from the casting process on the final product of the gas turbine impeller? I think this question is maybe Dr. Eni can answer this question first, or maybe for other presenter also maybe can answer this question. Please, Dr. Eni.
Okay, thank you very much for the questions. Actually, today's presentations is focused only on for the coatings technique to improve the oxidation resistance of turbine blade. Meanwhile, these questions is related to the process final product for the gas turbine, because as you can see that for the mechanical properties, a good process should be carried out to obtain a good turbine blade. But I'm really sorry, but I can give you a very good answer in this case, because I don't have any experience for the casting process for the turbine blade.
Okay, maybe Dr. Felix or maybe Mr. Bravola maybe can answer this question about the effect of the casting process.
Yes, Mr. Wahyu, same with Bu Eni. I don't have any experience in casting process. Sorry, I can't answer it.
Okay.
Same situation here. I only worked with polycrystalline casting rod superalloys.
Okay, maybe this question maybe we can ask again maybe in our next webinar maybe. Maybe Dr. N will hold another webinar on this issue, maybe inviting another presenter maybe.
Yes.
So we also have we also have another question from Miss Risma. Please, Miss Risma, you can ask directly to the presenter. I think Dr. Eni, I think.
Yeah. Okay. Thank you for the opportunity, Dr. Wahyu.
Where is Risma?
Yeah, I'm here. Okay, so I have two questions actually. So
please.
Okay, so the first question is so it in the previous presentation it has been explained that the effects of reactive element additions and also heat treatment condition is affected the oxidation performance. However, I'm curious about the effects of different heat treatment temperature to the oxidation performance, because it was mentioned that the alloy, the coating, which was heat treated at 1100 degrees C, was have better oxidation performance compared to the coating was heat treated at 1000 degrees C. But previously it was not explained why that happens. And then my second question is, if I'm not mistaken, it was said that beta nickel aluminum precipitates was formed on TBC, but I don't catch it. Was it formed during the heat treatment or was it formed during the oxidation? Okay, I think that's all. That's the question.
Okay, Dr. Eni, you can answer the question. Or should I?
Okay, thank you, Risma. Thank you. Okay, I can catch the question. May I answer, Dr. Wahyu, directly?
Yeah.
Okay. For the first questions, you curious that how the temperature, heat treatment temperature would affect for the oxidation performance, right? So at first we assume that we try to look at from the ternary phase diagram, especially for zirconium oxide at the relatively high temperatures, more than 1000 degrees C. Zirconium dioxide will transform to the cubic phase. But at all our samples, as you can see in the almost all slide of my presentations, after the XRD analysis, only a single tetragonal structures consists in the coated layer. So, but actually, more high temperature for the heat treated is good to get the properties of zirconium oxide and to transform to the cubic structure first. That's the answer. And the second question is related to the formations of beta nickel aluminum. So yes. Actually, as I presented in my slide, I explained the mechanism of the formations of the TGO layer already published as Chinese researcher in 2017, but it is general known that in the bond coat layer, if with the coating materials used is a nickel, cobalt, chromium, aluminum, or even though there is no cobalt, the existence of the formations of beta nickel ammonium could be identified. So in this case, because we try to evaluate our coating system from the surface, so there is a limitation using the XRD analysis. Therefore, in the all XRD results, we cannot identify the beta nickel ammonium in our samples. But actually, if I have already have experience using the TM, try to evaluate each layer, but I didn't show you here. So it means that in the coated sample, so after heat treatment, the beta nickel ammonium can be formed for the bond coat layer.
Okay, thank you, Dr. Rani.
Thank you, Risma.
Okay, thank you for the question. Okay, we also have another question from Mr. Halason Sinmanjuntak. Actually, I'm not quite understand about the question, so maybe Mr. Halason can ask directly to Dr. Annie about the question. Mr. Halason? The question is about which one is more important. I'm not quite understand about this. Oxidation resistance or temperature oxidation.
Oh, I see.
Okay.
I can guess it. I can catch the question.
Okay. No. Mr. Halason,
sorry, I can't hear your question, but I connection. I can hear your question, but I can the connection.
Okay, maybe I can catch the questions, Mr. Halason. Yeah. Thank you very much for your question. I try to simplify again the questions. So in the oxidation test and the heat treatment process, right? So in the case of our samples, correct. The heat treatment process, okay. So the heat treatment process should be carried out before the oxidation test. So the oxidation test is only for the to understand the performance of our coating samples. So in order for the heat treatment, we try to get a more denser coating layer. So if we have a good layer with dense, less porosity and something like that, so we can control the diffusion of oxygen during the oxidation test. So that is a different process, right? So both of them is very important for our coating samples. So the sinter treatment and the oxidation test, that's very important.
So both is important, but cannot be. Is it both important, right? So we yes. we can neglect one of them, right?
Yes.
Okay. So is there any other question from the audience? Maybe if there is no other question, I have one question. Actually, this is maybe how to say. This is a question from the commoner like me. I'm not an expert in this coating process, but I have one question. If we have to choose between adding some thickness in our substrate material and add some coating layer, which one is how to say economically efficient? Between if we have to add some additional thickness from of the substrate material and add some thin coating layer, which one is economically efficient? in how to say, in the point of view of maybe commercial business, which one is more efficient? Maybe for three speakers, I want to know the opinion of the presenters. Maybe from Dr. Felix, maybe you have some opinion.
So the difference, what's more economical, whether the coating layer or, sorry, what was the other one?
If you have, for example, if you have a substrate material, for example, about, for example, 10 centimeter, but if you want to prolong the lifetime, for example, you add, for example, 5 centimeters, and another option is you just use 10 centimeters substrate and you add some thin coating layer. Which one is more efficient?
Ooh, that's a tough one. I would say the base material pretty much determines the strength of your structure. Let's say a disc, for example, and then with the barrier coatings, my understanding is that you can increase the lifetime. So one is giving you the operational temperature, the other one, because the coatings are much more high temperature resistant, probably determine the lifetime. Would be my guess. So they need to play with each other, right?
Okay.
So can I add the answer?
Okay.
So from my point of view, yes, this is a very difficult question actually, because we have to consider the economical aspect for this research work. But as you know that if we add the thickness of the coatings layer, functions of the source, the fossil fuel source. So if that require, it will make a high cost for the operations. So for the TBC systems, as I already presented before, for example, for the bomb coat, the maximum or the average thickness is about 200 micrometer. So if you add more thickness, it will be a less functions for that layer to give a good performance. Yeah. And also, for example, for the top coat ceramic layer, it's about 300 to 1 millimeter in thickness. If you put more, it means even the ceramic layer has a low thermal conductivity, but more thickness giving less efficiency for the TBC system itself. So just follow the requirement of each coatings for the thickness, because at this field, if the projects in the power plant industry not to follow the schematic of this coating layer, especially in thickness, so I think it will be affect to the consumptions to the fossil fuel as the source of the power plant.
Okay. So we also have to consider the fuel consumption, right?
Yes.
Okay. Maybe Mr. Bravola have another point of view, maybe.
Sorry, I got unstable connection. Can you repeat the question? I just get which is more economical between coating and what?
So for example, we have the pipe. The thickness is about 10 centimeters, And which one is more efficient if we add, for example, additional 5 centimeters for of the substrate, and also we can also have add some thin coating layer, maybe around in the order of micron. So which one is economically efficient?
Yes, from my point of view, adding answer from Mr. Felix and Mrs. Annie, there is some parts that will be good if they are to be coated and in performance and in their economical. Okay, but sometimes there is part don't need coating. Okay, in point of view from HVOF coating, it's more economical if the part is to be coated. From your example is pipe. Okay, let me take some part like wall tube boiler. Okay, wall tube boiler, if the process manufacture, if the specification is high, the cost production will be high too. But if they use common material and then coated with thin layer, it will be more economical. Maybe like that.
Okay. I think this is because this question is very important for practitioner in industry. Yes. Which one to choose between adding some substrate and also applying coating layer. So ladies and gentlemen, we already finally we come to the end of the presentation. I would like to say thanks to all of the presenters for the informative and interesting talk, and also for the audience for your active participation. I hope the presentation here will be beneficial for everybody, for every one of us, and thank you for your attention. And before we close this session, I would like to have some photo session, maybe for the host, maybe to take the photo from each page. Mr. Basir, can help me? Okay, for all of the audience, I hope you can turn on your video. We can have a photo session now. Mr. Basir, already?
Wait a minute.
Aba-aba, Pak.
Mas Basir, sudah?
Kayak 1, 2, 3 gitu.
Oh gitu, oke. I will count maybe for the first page first. 1, give your smile. 1, 2, 3. Okay. Is it already, Mr. Bashir?
Ya, Pak, ya.
Okay. For the next page. Page 2, give your smile. 1, 2, 3. Okay, Mr. Bashir?
Ya, Pak.
Okay. And the next page? How many page? How many page here?
3 page.
3 page, okay. Okay, for the last page, Mr. Bashir, ready? Okay, give your smile. 1, 2, 3.
Oke, sudah, Pak.
Okay, thank you for attending this webinar. I hope we can meet again in another webinar, and on behalf of the head of Research Center for Physics, I I would like to say thank you for the attendance, and we hope we can meet again in another webinar, and also keep doing well in this pandemic situation. Thank you for the attendance. Good afternoon, everyone. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you.
Thank you so much.
Thank you.
All of participants.
Bravola, thank you.
Thank you, Bu Eni.
Felix, thank you so much.
Thank you, Mr.
Pandi,
Felix.
Pak Bravo, thank you. Bu Rika.
Ya, Bu Eni, thank you.
Terima kasih.
Thank you.